We all know the different characteristics of gases. In the discussion, you know that you can remember that gases, they are free to expand and they expand infinitely, and they have fluidity. Particles slide over one another, act like liquids. Thus, liquids and gases are considered to be both fluids. They have also low density and compressibility. That's why gases cannot be seen. Volume can be decreased greatly because of their big space from one another. And they diffuse and effuse. And if you remember, when we talk about diffusion, diffusion means gases are always randomly moving, freely mixing together with other gases. Effusion, on the other hand, is the process by which gases move out of a small opening. There's a tiny hole where gases escape, and the gases that are small and light diffuse more quickly than those with larger masses at the same temperature. Now, for this lecture series, we're going to talk about diffusion and effusion, particularly effusion, the rate at which a gas or gas molecules pass through a certain opening. So we're talking about rate now, which is very much related to the concept of it. Now, diffusion is just the random mixing, as seen in this diagram. It's just the random mixing of a particles from one source, and then it's going to speed up and mix up with the rest of the particles. That's why you can smell a certain gas if ever there's a release of that at a certain corner of a room, and then eventually after some time you're going to smell it. That's diffusion. On the other hand, you contain a certain gas and then you put a hole where they can possibly escape. That is effusion, because that tiny hole will give way for the gases to escape through that hole. The rate at which these gases escape is what we call effusion. And the law that governs that is what we call the Graham's law of effusion. Rates of effusion and diffusion also depend on the relative velocities of gas molecules. The velocity of a gas varies inversely with the square root of its molar mass. When we talk about velocity, we're talking about movements, and we acknowledge that gases are always moving, so they have a lot of kinetic energy. And you know that kinetic energy's formula is equal to one half of the mass times the square of its velocity, or one half mv squared. If we're comparing two different gases, how they escape through that hole A and B, we have the kinetic energy of A, which is equal to the kinetic energy of B. Why are we equating them? Because they are at the same temperature. Even if the two gases have different composition, they have different identities, but because they are placed in a container where they have the same temperature, so we can assume, because temperature is defined as the average kinetic energy, that means that the kinetic energy of gas A is just equal to the kinetic energy of gas B. However, their rate may differ because their masses are different, because they're two different gases. But overall, the Ke is just the same because of the same temperature. So how do we derive now? Now, please remember first, before we derive Graham's law, that rate, when we talk about rate, it's always per unit time. But what is per unit time? It's the amount of gas that transfers to a certain distance per unit time. How many gas molecules are traveling at that particular distance per unit time? That's always the definition of the rate of effusion, or sometimes the rate of diffusion. Take note, that's basic. That's just like velocity, which is the displacement per unit time. We just term the displacement to be that amount of gas that travels to a particular distance per unit time. So it's considered per amount. Going back to our kinetic energy, how do we now derive kinetic energy's formula for Graham's law? So let me show that to you. We know that our assumption is one half of the mass of gas A times the square of its velocity is just equal to the kinetic energy of gas B times VB squared. Okay, now let's put the same variables together. Now, because they have common one half, we can just remove the one half there. We divide both sides by one half, that's gonna get cancelled out. But we can never cancel out mass and volume because they're two different gases. So let's combine all the masses together and let's combine all the velocities together. When we combine, the result will be ma over mb. We transfer mb on the other side, left side, while on the right side, va gets transferred and it's going to be below vb. So that's going to be the resulting equation, putting all masses on the left and all the velocities on the right. Now, because I want to get velocity, for example, and these are squared, that means I can just square root both sides and I'm going to remove the square of velocity. Therefore, the final expression of Graham's law will now become VB, I'll just put velocity first because it's about rate, over VA is equal to the square root of the mass of gas A over gas B. So what does it mean conceptually? Looking at this formula, we can already say that the velocity of, for example, gas B is inversely related to the square root of its mass, or sometimes molar mass of gas B. So what does it mean? The bigger will the mass of gas B is, the smaller will be the volume, or the higher the volume of B is, the smaller should the mass be. So a smaller, lighter gas travels faster compared to a gas that is heavier and bigger. That's what it means. So velocity or speed or rate is inversely related to the square root of the molar mass of that gas. Okay? So in summary, you have to understand that Graham's law, sorry, in summary, we know that Graham's law now is about investigating the relationship of gas to the molar mass of it, the velocity and the molar mass of it. Sorry, there's some trouble here. Let me just escape from my slide and then there. Okay, so I'm gonna go to the final expression of Graham's law, which is rate, which is just the v that I just showed to you a while ago. The v of a over the v of b, velocity of b, is equal to the square root of the inverse of molar mass of b and molar mass of b of a. So when I say a or b, it's two gases that we're differentiating. So if your velocity of A is on the numerator on the left side, its molar mass should be denominator on the right side. And similarly, if the velocity of your gas B, whatever is your assigned gas B, is in the denominator on the left side, it should be numerator on the other side. Take note, this is just the only expression for Graham's law. So in summary, the diffusion rate of a gas is always inversely proportional to the square root of its molar mass. The bigger the molar mass, the slower it effuses. More massive particles move at a slower rate compared to the ones that are lighter by mass. So that's it for Graham's law. Watch out for the next video so that you learn how to apply the equation of Graham's law in problem solving. So that's it for now. This is Madam Narca saying, don't stop learning, relearning, and unlearning. Bye for now. God bless you. Please like, share, and subscribe to my YouTube channel. Bye bye.